Okay, so it turns out that my first video was way too long, so I gotta find a way of making this quick. So simply, problem number one, XYZ direction, I put Z being up, Y to the side, X being towards you, or like towards the reader. But I only used 2 dimensions instead of 3 because I thought 2 dimensions was good enough. Acceleration is, I drew it in the Y direction, and so acceleration is like this. And so I drew two, one when it's stationary and one when it's when the acceleration is affected, and then the constant pressure line is also drawn. And as you definitely know, along the constant pressure line, it's the same pressure. So for part A, you wanted us to find the pressure distribution on each side of the tank, which are perpendicular to the acceleration direction. So since I drew it in 2 dimensions, the top and the bottom are the only orthogonal sides. So those on the top, the pressure distribution, it's uh it's constant. So therefore, the pressure on the top is P atmosphere, 1 atm, or 101 325 pascals. At the bottom, I had difficulty at the bottom, and so for the bottom, I came to the conclusion that P is equal to PATM plus rho GH. Um, for stationary level fluids, that was the only thing I could think of. But that doesn't really explain, because there's a difference of there's different levels of height, there's different h's. So I'd imagine that you would have to do like an integral to sum all of them eventually or somehow, but I personally do not know how to do that. So I couldn't think of anything, so I just came up with P at the bottom is equal to PATM plus rho GH, and I don't know. Okay, and then you asked us to find the slope. I used the formula that I wrote from the notes. dz over dy is equal to negative ay over g plus az being 0, ay is equal to 0.2 g. So then this simplifies to dz over dy is equal to negative 0.2 g over g plus 0, or over g, which it gives you negative 0.2 g over g. The g's cancel out. Dz dy is equal to negative 0.2. Problem number two. Oh, I gotta go faster. Problem number two, I drew point one at the surface of the gas tank, tank of the fan, and point two, the siphoning gas tank, and then the end of the hose, 0.75 meters. I drew point one to be 0, like the surface to be 0. I need to write it in. I might forget that the diameter is 4 millimeters, which is also 2. Which means the radius is 2 millimeters, which also means that the radius is 0.002 meters. Density of gas 750. You gave us that, and then I assumed that P1 is equal to P2, which is equal to P atmosphere. This is for part A, by the way. V1, the velocity at point 1 is 0, and then the velocity at 2 is also so point 1 is at the surface, and point 2 is at the end of the hose. That's very important. I'm sorry. V2 is what we're looking for. P1 is P atmosphere. V1 is 0. This simplifies to V2 is equal to 2g, the square root of 2g, z1 minus z2, which is just 0 minus negative 0.75, which gives us the V2 is equal to 3.84 meters per second. Using that and the flow rate formula that states that velocity times area gives us the flow rate, I found that the flow rate was equal to 4.82 times 10 to the negative 5 meters cubed per second. Then I played around with multiplying the flow rate times the velocity or something similar to that, and I got that I would have to multiply not the velocity, the volume, I'm sorry. I would have to multiply the volume times the reciprocal of the flow rate, and that gave me, to get time, that gave me a total of 62.2 seconds. It's all written here, you can check. It's just I got a time pressure and I'm trying to move fast, or else I won't complete the 100, whatever. Part B, So I did Bernoulli's equation again. The point one is at the surface of the gas tank again, but this time point two is at the max. So the max, which is 2 meters, and 1 atm is 101,325 pascals. I said the pressure P1 was PATM, but we were looking for P2, and V1 is 0, and V2 I got from the past equation the same, which is 3.84 meters per second. Simplified all of that, got that P2. No, got that P. Might as well give you the number. I'm sorry. That P2 is equal to 81,092 pascals, or 91.875 pascals. Rounded up 81,092 pascals. For C, same idea, but what's it called? Now we have V2. We got V1 is equal to 0, V2 is equal to 3.84, P1 is equal to P atmosphere, and you gave us a pressure. So P2 is 80,000 pascals, and then Z1 is still 0, and Z2 is the unknown. Used Bernoulli's equation again, and then worked that out to be that C2 was equal to 2.15 meters. So that's it, and I hope I didn't go over